Okay, now we are going to discuss about the famous transformer model architecture. Up to now, we have discussed about the basics of neural networks, single neuron, single perceptron, single layer perceptron, multi-layer perceptron, convolutional neural networks. Before that, we learned about shallow neural networks, deep neural networks, then convolutional neural networks, and then we have discussed about recurrent neural networks. Then there are extended versions like gated recurrent units, GRUs, long short-term memory units, LSTMs. And now we are going to discuss about the latest deep learning model, which has paved the path to large language models, where the current AGI-like abilities are available with these models, right? So this transform model has not built from the scratch, or so it was not born in a vacuum, but it was developed uh, with the knowledge that scientists or the developers or the people who are researching about these topics uh, that have already gained the knowledge about uh, convolutional neural networks, other neural networks, and these sequence models, right? So they were trying to improve the sequence models, and they have used some concepts that were already used in convolutional neural networks, and they have come up with this bit complex model, which can be mainly used for uh, sequence models, and also at the uh, latter part of the lecture we will see how it is going to do the stuff that are already done mainly using convolutional neural networks as well. So this is the state of the art model, the basic model that we have at the moment. So there are variants of these transform models as well where people have developed. But at the moment, if you think as a basic concept, the basic model concept, this is the basic model concept that is in the cutting edge of the technology. So I say it's as a technology because uh, we haven't proven this is a science, right? So this is in this deep learning, people are developing certain algorithms, certain formulas, and they are trying to use them for learning, right? And some of them are getting successful and they become the prominent models, and they are given some names and they are getting popular, right? This is one of them, right? So there's no magic in this model, but this has helped a lot to uh, achieve the capabilities that we have uh, at the moment with related to artificial intelligence. So that is why we are going to learn it. So before that, we have to learn what are the problems or the limitations uh, that people have found that were there in recurrent neural networks. The first thing is the slow computation for longer sequences, because uh, as we have discussed, when it comes to recurrent neural networks, LSTMs and GRUs, all because there are multiple time steps, you can't process the process each of the layer in parallel, uh, because that is a main uh, that is an inherent nature of sequence models. We are not only in sequence models but also in deep neural networks. When you are learning or back propagating or forward propagating, you have to learn or predict in a sequential manner but not in parallel. So when there are multiple time steps, the computation cannot be parallelized, or they cannot be done in parallel using parallel hardware. So the parallel hardware that are developed at the moment are not useful when you are using recurrent neural network or their derived models like GRUs and LSTMs. And the other problem is that when the common things that we know about the problems that are arising when the neural network is getting deeper and deeper. One is the vanishing gradient problem, and another one is the exploding gradient problem. Right? However, GRUs and LSTMs could address most of the problem up to a certain level. So using GRUs and LSTMs, you can use much longer sequence models, but still that problem is still there when it comes to very long sequence models. Right? So this is one of the things that is still there, but not significant, because we can do something significant with GRUs and LSTMs at the moment, but this is still there, right? And when it comes to the other main issue with all the RNNs, LSTMs, and GRUs is that when you are when it is processing the information has to be passed from the hidden state. So the information that is passed from the history is limited only to the vector size of the hidden state. So unless you are increasing the hidden state vector, you cannot increase the memory that is brought from the history about the history. Right? And when the information is passed in several time steps, it is getting eroded, or the history get forgotten after many number of steps. That is another problem. Right? In the sequence models, we have discussed that in order to handle these problems, people have found that just passing the information from the history to each of the models, to each of the time step, is not the only way. Instead of that, we can follow what humans are doing when we are going through a sequence of words in a text, where we are paying attention only to some of the terms in the text. So they have developed attention mechanism for existing RNN models, RNN, its derived models, using, as we have discussed, where you can have bidirectional models, and then we can generate the attention for each of the index, and then we can apply this attention in the unidirectional sequence model, and then we can get much higher performance when it comes to that kind of uh, attention-based sequence model. Right? However, we have observed that uh, sequence models with attention needs much computation and memory, where when the sequence size is increasing, the memory and computation power increases quadratically. That means it's increasing in the power of 2, as a power of 2. That means that is a problem when the sequence length is increasing. However, because that is successful, it can be used. In 2017, in the Google's set of people, researchers have released a paper known as Attention is All You Need, where they have paid only much attention to the attention in the sequence, uh, instead of uh, getting instead of focusing on the information flow through the sequence model. Right? How does this information flow happens in the sequence models? You know, right? So when you have a sequence model, you have some hidden information passed to the next input, next time step, and so on. Right? The information is passed in the hidden state, cell state, or activation, whatever the name you know, right? Whatever the name you use, this hidden state is passing the information. Right? This is what they have found was this is not really required. And these units are already also not required, right? We can make a single model where we only take each of the words or each of the tokens or each of the input events, and if we can pay attention only to the most relevant uh, units or most relevant inputs, then we can make a better sequence model. Now the problem is, if we remove this information flow, how do we know that this is the first event, this is the second event, this is the third event, and so on? That is the problem, right? So if we remove the sequence and if we just consider all these input vectors as just a set of vectors, then its sequence is getting deleted, right? So this information will not be there. So in this paper, they have proposed a different way to encode the positional information, right? This is the first position, this is the second position, this is the third position, and so on, right? So you can encode this positional information in a different way, where you are modulating kind of this positional information in a sine wave, and you add this into the encoding or the vector itself, right? That is what they have proposed. Instead of implicitly developing a model where the sequence is inherently there, like in recurrent neural networks, LSTMs and GRUs, what they are proposing is just have the set of input vectors, use their positions, and modulate, or uh, using these positions, just use several sine waves and then modulate these sine waves and create some signal depending on the position, and then add that positional value into the vector itself. So then the vector will get somewhat distorted, but that would be later identified by the network and it would be corrected. But this positional information is not explicitly introduced into the neural network, and this would work very well because not because the positional information is removed or given a lesser priority, but because we are highlighting how the attention should be given and what are the uh, positions that you should be given attention in each of the context. That is the idea in this attention is all you need paper that was published in 2017, and that is the birth of the transformer model. So in this lesson, we will be discussing how the transformer model is designed and how it is working and why it is working and its design and so on. This is what the paper has given itself. In the paper itself, other than these two blue regions, the paper has given all the diagrams as given here, instead of just naming them as encoder and decoder. It has given the diagram as follows in the paper itself. So this is the architecture of the transformer model. In this lesson, we will be discussing what each of the component does and what happens in each of them. As you see, it's a bit complex, much more complex than any of the models that we have learned up to now. But it is worth learning this model, and once you learn each of the component individually, you will understand it is nothing significant, but you can understand it and you can use it without much issue, right? So for making you easy to understand on this model, I have divided the whole model into two components, one as encoder and the other one as the decoder. In the sequence models, we have discussed that we can have a sequence models. We can generate sequence models like this, where when you want to translate Japanese language words into English language or something, you can give the Japanese language words like this. So where this is the encoder and the hidden state of encoder is passed like this until the end, and at the end you can get the vector which is encoded in the message or what is there in the language, the meaning of the language in, into this vector, right? So this is the encoder part as we have learned, and this is passed to the decoder where you can generate the English words. The hidden state is moved from one timestamp unit to another and generate English words like this until it generates a end of sequence token. It may be a full stop or any other token, right? So this is known as the decoder component. This is the English output. This is the Japanese input. So replacing this encoder decoder architecture, this transformer is also developed with these two architectures, where the encoder is encoding the input sequence like this one into encoded format in this part, and then it is decoded by this decoder, and the output can be given in this softmax layer, right? So in the softmax layer, we have a vocabulary, and from the vocabulary, you can select what is the next word that is corresponding to a particular vector, and using that vector, you can generate more and more words. That is how the words are generated in a large language model in simple. So let's see how each of the term, each of the component, and what each of them are doing, right? So in this diagram, you can see we have the inputs, which can be a set of word inputs or token inputs. When it comes to this paper, it is about natural language translation. So it is actually a sequence of words. The inputs are words and they are encoded using the embedding, and it is added with the positional. So it is added with the positional encoding, which we will be discussing later. And there would be the encoder units that can be represented in this format. And there can be n number of such units that are uh, stacked one over the other, right? So this is in this diagram we have only displayed a single encoder, but there can be multiple encoders stacked one over the other, something like this. First encoder, second encoder, third encoder, and so on. Right? N times encoders, and this final output is given to the decoder like this. The decoder also, the output is generated, and the generated output is fed back into the and appended to the input of the output, that is known as the shifted right outputs. And so we will be discussing what does this mean really. right? And this output is already also added with the positional encoding, and it is added to this decoder component, and there can be n number of decoders, and finally the output is given to this linear layer so that it is mapped to the vocabulary size that is required for this softmax function, right? So the idea is that the output from this at this point can be arbitrary number of it can be a certain number of a certain dimension vector, right? But the vocabulary at the softmax layer can be different. So this linear layer would map from the output in this layer in this position to the vocabulary size that is required for the softmax classification, right? So vocabulary is what is the next word that you should be generating. So that is the idea of this transform model, which is given in this paper, right? So this initial paper, it is the transform model is introduced for natural language translation purpose, where you give a certain uh, text given in a certain language and it is translated into another language. So you give the input as inputs in this location and the outputs are generated in this location. Because the words are generated one by one, when a certain word is generated, that particular word is appended to this output of this decoder, that is known as the shifted right output. It is something like this. So you start with empty inputs. So first you give the inputs from the Japanese language, for example, you give a certain sentence, and that sentence with we give first with outputs as first start token or something. Right, this is the start token, and this would predict certain with the given encoded input. It would produce some token, right, or a certain English word, which is appended to the start token, something like I. Something like I like to eat ice cream or something like that. So then again with start token and I token, this would generate another token, another word, which may be I like, I like or something like that. Right? I like. Then it is also appended to the this output sequence where we are using start, I, and like tokens and generate another token, right? I like, then it may be two. I like to, then it may be eat ice cream or whatever, right? Something like that. When the full stop token is generated or the end of stream token is generated, this generation process will be finished. That is how the natural language translation happens in a transformer architecture. Actually, this is how the sequence to sequence modeling or the encoder decoder model is generating sequences. Like when you are generating a certain token, it is given as the input for the second time step, and this output is also given as the third time step, which is the second token generated, and so on until the end of sequence token is generated. This is how what you can do with LSTMs as well. Actually, before the transform model was invented, they have used LSTMs for natural language translation. So in the earlier time, some time ago, before the transform was invented, they were using multi-layer. We have discussed about deep sequence models, like deep RNN models. So similarly, we can have like 7, 8 uh, layers deeper LSTM layers for translating from one language to another language. That is how the natural language translation was happening, even in Google. in the Google translation was earlier using multi-layer LSTM layers for in this encoder decoder architecture. This was the architecture which was used earlier before the transform was invented. So after the transform was invented, they have used it because it can do it better. So we will learn how the transformer model is working. So we will go part one by one, right? So before, in the first, we will be discussing about this encoder, the parts from starting from here to the end, right? And we will then we will discuss about the decoder, and we will start from here and move upwards what each of the components are doing. We are not going to discuss about the known items like feed forward layers or add and normalization. So we will discuss what is add and normalization once, and we will not be discussing again and again, right? So you can see feed forward component is here, and it is also there, right? So you know what is a linear layer, right? So it's a single layer neuron layer, right? You know what is softmax function, right? So once you learn about add and normalize, there you can see that the normalization, there you can find it again, right? So once you learn about input embeddings, you know that is the same thing that you do in output embeddings too, right? Once you learn about positional encoding in the encoder, you know that is the same thing that is happening in the positional encoding in the decoder as well, right? So once you learn about this multi-head attention, you know that is the same thing what is happening in the multi-head attention in this component as well, other than this difference of these inputs. Like in here, you can see there are three inputs that are coming from the same input, but here one input is coming from the previous layer and the other two inputs are coming from the encoder output, right? So this is known as a cross attention, and this is known as the self attention. So we will be discussing what each of them are doing. And these connections are residual connections or skip connections that we have learned in the ResNet architecture in convolutional neural networks. So we know why it is used and how it is done. Okay? So we will try to discuss a little about that as well. So let's start with the encoder input and embedding. Right? So what is this input? This is the text input that we are giving to the model. Right? So these are sequence of tokens or a set of words, right? That is used in NLP, natural language processing. Because we can't use the exact sequence of words in natural language into the neural network, we have to encode them using input embeddings. We have discussed what are the embeddings. It's known as word embeddings used in natural language processing, where we can encode each of the word with a certain vector which we have found, right? So we have earlier discussed that we have discussed how to encode the word using one hot encoding, and then we discussed no one hot encoding cannot be used because it is too large and there's no meaning in it, right? And then we have discussed how to include the meaning for each of the words, and with lesser number of dimensions we can develop a much meaningful vector known as word embedding. So instead of for each of the words, after we have tokenizing the input, tokenizing means we split the uh, sentence or text into different words or pieces. Then we encode each of these tokens into different vectors in numerical format. That is known as the word embedding. Embedding the or vectorization of the words. Right? So there are two types of word embeddings. One is known as the pre-trained word embeddings and sub-word tokenization. The pre-trained embedding is what we have discussed mainly, where so the process that I have explained about the word embedding is not the actual way it is used, because it is an fully automatic process where you give so it is an unsupervised learning technique where you give a large amount of text, so it can automatically learn from a large amount of text by masking some of the terms and so on, which we would not be going to discuss. So that is known as a pre-trained embedding. So you give a very large corpus. Corpus means large amount of text, uh, and then with this text, it can train with a lot of time, with lot of computation power, and it can generate a set of vectors for each of the words or the tokens. So GLOW and Word2Vec are two of the well-known such pre-trained embeddings. So you can download these Word2Vec vectors or GLOW vectors from the internet, and then you can use them to vectorize each of the words. However, those are pre-trained. That means that those vectors are fixed in its meaning, right? But when it comes to practical applications, different words are having different meanings depending on the context, right? For example, I can say, uh, I may like to go home in May. So the first May is about something else. The second May is a month, right? We know because by looking at the surrounding words or its context, we can understand this May is about a meaning, something similar to could or would, something like that. This May is not something like that. It is a month, name of a month, right? So depending on the context, the application of this token may differ. But when it comes to word embedding or pre-trained embedding, the word may have a single set of single vector, right? Whatever the application it has. So when it comes to transformer models, which is a much more advanced versions, we have better embedding techniques such as uh, subword tokenization. So one way is using that we can train these kind of embeddings uh, from scratch, but for specifically for these transformers, there are specific subword tokenization algorithms are there. So where you can uh, tokenize the strings, not actually into words itself, but even as pieces of words as well. For example, if we think about a certain input, right? Like or if we take an example like this word, like natural language processing, right? So this ing is a commonly used word piece, right? This ing is used for running, eating, and so on. So ing is taken as a word piece because it is highly using, right? This pro is also another uh, piece of word that is used in different locations like processing, proclaiming, procurement, and so on. And proc may be another word piece, right? Process may be another word piece. The processing is another one, right? So whatever the largest token it has, so there are different ways of tokenizing these words into different pieces, right? Not only as complete words like for example, natural as a single token, language as another a different token, and processing as a different token. So that is the traditional pre-trained embedding technique, where each of the word is given as a is considered as a single token. But with subword tokenization, we can uh, tokenize even several parts of the even small parts of a word as a single token. Actually, there are certain techniques that some of the researchers have experimented where we can use each of the even a single letter can be used as a single token. But when it comes to this kind of implementation, then the sequence length would be too large. So then there would be a problem of too large sequences where the learning process would not be easy, right? That is why the single letters are not used. But if you in the future, some believe that in the future we may be able to use single letters and single numbers like 1 2 3 a b c d, and these letters and numbers can be used as tokens as well, right? Instead of using word pieces at the moment, right? So this is also an evolving technology. So when it comes to this to transform model, we are recommending of using this subword tokenization, such as byte pair encoding and word piece encoding. So these are two of the widely used tokenization techniques where you can use uh, them for transformers. The one of the advantages of using this technique is that this is this can handle most of the out of vocabulary words, right? The problem with most of the uh, word embeddings is that there are a lot of out of vocabulary terms. Out of vocabulary terms means the words that are not there in the vocabulary, because when you are training uh, word embedding, all the words that are in the world may not be there in the vocabulary, right? For example, when it comes to a technical document, there may be some technical terms that are not used in the word embedding. In that case, using this byte pair encoding and word piece embedding, you can construct the unknown word by taking into smaller pieces, right? If you don't understand, for example, what is embedding, you know, ing we know, right? Embed we know, right? Maybe you can use embed and d and ing as three tokens instead of using embedding, because embedding is not in the vocabulary. So instead of using embedding as a single uh, token, you can use these three tokens and continue with the transform model. So this is another advantage of using subword tokenization instead of using full word tokenization. So once you have encoded the words that are given in the text in this step, then we can move to the second step, which is positional encoding. So let's move into the positional encoding. So before that, so let's first look at how each of the word is encoded in whole word encoding, whole word embedding. Sorry, whole word embedding. So suppose your word sentence is your cat is a lovely cat, right? So you can tokenize each of these words into different tokens. The first token is yours, the second token is cat, the third token is, fourth is a, fifth is lovely, the sixth is the cat, the sixth is cat, right? For each of these tokens, you can give different IDs, right? Yours is given the ID, positional ID, as 105, the cat it is 6587, and so on. For each of the word, there would be an index or an identity number which is in the vocabulary. Right? From this vocabulary identity, you can find the exact embedding in the embedding table. Right? With word embeddings, if it is a pre-trained embedding, you can find what is the embedding. So embedding is a vector like this. Right? If it is an subword embedding, subwording encoding, it would not be a full word like this. It may be like a U, like OUR, YNOUR, or something like that. Right? Not a full your word may not be a token, right? So it may be like a token may be divided into U as one token and R as another token and so on, right? So then it would be the first token and this may be the second token and so on. Right? So whatever the token that you are using, each of the token is mapped to a embedding vector. So in this case, the vector size is 512 for this example. Right? Once the embedding is calculated, you have to add the positional encoding as we have discussed earlier, where we have to add the information of each of these word which is related to the position of the or the index of the word in the sentence. Right? For example, if you look at this sentence, this is the first word, this is the second word, and so on. This is the third, fourth, fifth, and sixth word. Right? These are positional information. Right? For each of the positional information, you can create an embedding. Right? It's known as the positional embedding, positional encoding. Right? This positional encoding is actually independent from the words itself. That means either it is yours or cat or whatever. The embedding for the first position is a certain vector. Right? Embedding encoding for the second position or positional encoding is a certain vector. Right? So once you have calculated the positional embedding vectors, right? Positional encoding vectors, you can use it for all the sentences, whatever the sentences, whatever the words they are in the sentence, right? So this is how you do it. So if it is either the sentence 1 or the sentence 2, we are using the same positional embeddings. Right? So positional embedding is computed like this. For the odd numbers of the positions for each of the word, for the odd, if we the first positional encoding is known as PE00. The first parameter is position. Position means whether it is 1, 2, or 3. This is the position. 1, 1, 2, 3. These are the positions. And the second one is the I, which is the index in this vector, right? In the positional encoding vector. For the odd numbers, you can look at the red color arrows, right? For the odd numbers, we can use this formula to calculate the positional encoding. For the even number of encodings, you can use this formula to calculate the positional encoding. Right? So when it comes to this sentence or this sentence, love you, your cat is, or I love your, or whatever, the positional encodings are the same, right? So if you look at this sentence, sentence one's first word's positional encoding, it is PE00, which is same as the PE00 in the second sentence, because the position is 1, right? For the first index, for the first position, first index is PE00. For the for the first sentence, first position, the second index is PE01. Right? So it has to be calculated using this formula. So I'm not going to explain much more deeper into how each of these uh, formulas are generating these positional encodings. So what you have to understand is that these formulas are generating sine waves and cos waves, right? In different frequencies. One is creating a high frequency output like this. Another one is creating another much higher wavelength sine wave like this. Another one, another value would be having even higher wavelength, and so on. Right? For each of these positional embeddings, you can have the values in this one first, and this one second, and this as the third value, and so on. And they are added to each of these positional encoding. We are not looking how they are developed. We are not going to visualize it, but if you are interested, you can look more into it. How these sine waves are added and they are used to distinguish between the positions, right? So the idea is that we want to distinguish this is the first position, this is the second position, this is the third position, and so on. Right? So what we are doing is we are using this position. We are calculating the positional encoding vector, right? Which is this vector, and you have to add it to the input embedding vector, so that the positional information is also added to the input embedding. Right? If you are using the pure input embedding, this transform model would not understand, would not know whether this word is the first word or the second word or the third word. Right? But by after adding this positional encoding in this step, later stages can understand, yeah, this is the first word, this is the second word, and so on. So we are not going to see going to explain how each of these uh, sine waves are affecting at it, but you can have some intuitive understanding. This is how it is happening. Right? So then what we do is we take each of these words, first word, second word, third word, and so on. Your cat is a lovely cat. And then you calculate all the word embeddings for each of these tokens, each of these words. And also you calculate the positional embeddings or positional encoding for the positions, right? Actually, these positional embeddings are not calculated for your words, but for the positions, right? Actually, the position encoding calculated for first position, second position, third position, and so on. These are the values. And then what you do is you take the embedding and add the positional embedding to the word embedding, and then you get the encoder input, right? If the word embedding is size of 512, then the positional encoding should also be having the size of 512, and then the encoder input would be having the vector of size, vector of dimension 512. So this is what really happened, right? So you can see, you can cross check with these values, right? So when you are free, right? 1 plus 8 equals 9, and so on, right? So you can calculate this vector is added to this vector, and you can get this vector. So this is the vector that is going to be used in the from here, right? So now we have to go to the most critical or the most uh, tricky part, or the significant part, significant technique that is used in transformer architecture. That is the multi-head attention. So we will spend some time in this section where we would try to understand what is this multi-head attention and how it works. Right? In in the previous settings, we have in the previous slides we have understand that we take the text input and tokenize it, and then we calculate the word embedding, so subword tokenizing, and then we add some embedding in it, word piece embedding or something, and then we calculate the positional encoding for each of the positions in each of these words or tokens, and then we add it, and then we calculate the uh, input vector, input embedding. We can call it as X, right? In this case, right? And then we are providing them it to the multi-head attention layer in the encoder. So this is the encoder, right? There can be multiple n number of encoder units in the actual encoder, right? So only in this case we are only drawing only a single unit of encoder, right? In this encoder, first part is multi-head attention. So what is this multi-head attention? So before we learn about the multi-head attention, you have to learn about the single head attention, right? Or simply the attention, right? Single head attention is attention. So once you have multiple single head attentions, it is known as the multi-head attentions. So not only several single head attentions, but some difference, right? So we will discuss that as well. So when it comes to single head attention or attention, this is the formula. Just look at it and try to understand it. Right? So suppose in the attention, when you're calculating the attention, there are mainly several types of attentions. In this case, in this encoder, right? Because this is an encoder, we are implementing this attention in encoder of the transformer. Here we are using the self attention. So this is the formula for self attention. Not actually self attention. This is the we are using the self attention in the encoder, but we are using the cross attention in the decoder. But for all of these attentions, this is the formula that we have to use. So what are these parameters? If you are familiar with some database queries or some key value database, key value pair databases, you may be familiar with these terms: query, key, and values. Right? So this is about searching a certain value from a key value pair database, where you can have a sequence of keys and values. Keys can be represented by key K, and values are represented by V. Right? Value is the real content. Key is a small key that is representing the value. Right? Keys are indexed, and the keys are mapped to each of the value. Right? So when a query comes, which is represented by Q, the query is also a small string, something like that, which is going to be mapped against all the keys in the database. When the query is, when you find that the key is mapping, the query is mapping to the key in the database, you can select this particular key value related entry, and then you can take the value part which is corresponding to this particular key value. Right? So what we are going to do is we are trying to find how similar this, how relevant this query to each of these keys in the database, and then we find what is the highest matching key in this database. Once you find this is the key value that is most matching for this query, then you can select this value, which is the value that we want from this database. This is what real, that is the technique that is what it is really used in this attention. So this because we are using the same value x, which we have earlier calculated for all the query key and value. This is known as the self attention. Right? So in the encoder, all the query key and value are equal to x. So in the multi-head attention, you can see there are 3 inputs, right? So actually these 3 inputs are corresponding to query, key and value. In the encoder, all 3 are equal to x, right? Now let's see why we are using this self attention. Actually, this self attention is um, born with the concept that which I have just explained. It is about querying a key value database, key value pair database from a query parameter. In that case, in the self attention mechanism, we are using all the x values, all the words against all the words in the context. That means when you are, say, you are giving a sentence like this, right? The animal didn't cross the street, something like this, right? Like the animal didn't cross the street because it was too tired. So now in this case, you can see those are not whole word tokenization. Those are word piece. Those are subword tokenization, right? The is uh, tokenized as a single token, and underscore is also there, and the animal is also token as taken as a single token. And when it comes to didn't, DIDN is taken as a single token, and apostrophe is taken as another token, and T is taken as another token. Right? Similarly, you can see that tired also, tire is taken as a single token, and D is taken as another token. Right? So what we do in the self attention is we take each of these tokens. For example, we take the it token because it was too tired. We take the it token. Actually, we does the same thing for all the tokens, and you take the it token. We are comparing the it token with all the other tokens in the context, right? All the other tokens in the context are all the other tokens that are in this sentence, right? So it is finding which value is most uh, relevant to this token, right? When it comes to it, what does it mean by it? Now we can see the connection is highest when it comes to the tokens, the animal, right? So then you can understand, yeah, these are the tokens that are relevant to it. And similarly, you can calculate all the you can find what are the most highest attention tokens that are there in each of these tokens in its context, right? Like the it, you are finding the attention tokens for all the other tokens as well. So that is the idea of, so if you think this as the Q value or the query value, right? You can find which is the, actually in this case we are using the same keys K and V and Q as the X, right? So because this is self attention, and then what we are trying to do is when you are calculating this attention, what we are doing is just look carefully at this formula, because this is the part of the transformer attention, right? So what we do is we take the multiplication or take the dot product of Q and KT. KT means keys transpose. We take the dot product of query value and the transpose vector of key vector. So what we do is we take the dot product of K and T. So the dot product is a measure of the similarity, right? If the uh, if the QKT is high, that means the similarity between Q and K are high, right? So then what we do is we have to normalize this value by dividing the dimensionality of K, because when there are many dimensions in either K and or T, because the K and T are in the same cardinality, that means both of them are having the same number of dimensions. So when the number of dimensions are too high, this value would be larger, right? So because of that, we have to normalize this token, normalize this vector by dividing it with the square root of the dimensionality of any of the vectors, right? This dk is the dimensionality of any of these vectors. In this case, the k vector, right? And in this way, you can find, and then what we do is we take the softmax, right? Softmax is used to give the attention to the largest, right? So we are not using the max. Actually, when you take the maximum value, you have to take max, but because this is a gradient descent optimization problem, we are not using maximum value because it is not differentiable, and because it is not continuous, it cannot be, it is not differentiable. So we are using softmax function, which can be differentiated and learned, right? So we are using softmax to find which key is much more, so to find whether the value is maximum or which is the matching value, and if that is the case, then we multiply it with the v value or the value. So if the match is so high, that means the query and the key are matching very well, then the softmax would be much more closer to 1, and 1 multiplied by the value, you will get the higher value for that particular combination, query, key, and value. So for the matching key value, you would have a much higher value for this attention calculation, right? So that is what really happens in this attention calculation. So if you look at the calculation, this is how it happens. If the query is having the dimensionality of in the shape of 6, 5, 12, and it is multiplied by kt, or taking the dot product, is having the dimensionality of 5, 12, and 6, and it is divided by the dimensionality, which is 5, 12, square root of 5, 12, and you will get a matrix like this, which is in the shape of 6 by 6. And then you take this softmax value and multiply with v, right? So this is the same matrix here, and then we multiply it v. This is a 6 by 6 matrix. V is a 6 by 512 matrix, because all the q, k and v are 6 by 512. kt is 512 by 6 because it's a transpose, right, of k. By multiplying this matrix with v, you get a 6 by 512 matrix, which is the attention matrix, which can be then used for add and normalization step, right? So we will see what is there in this add and normalization later. Before that, we have to move forward about the multi-head attention. So we have learned about the single head attention up to now, where you can calculate the attention with this formula, right? Softmax QKT divided by square root of dk times v. This is how you calculate the single head attention, or simply the attention. But now so this is something similar to the filters that are used in convolutional neural networks, right? So if you think about a filter, how the convolutional operation happens with a certain one operator or with one filter, what happens is this is corresponding to this is analogous to the attention in transformer architecture. So when you want to increase the number of parameters, that means when you want to learn more with more number of parameters, you can, in the convolutional neural network, you can add the number of convolutional filters, right? You can have 2, 3, 5 or many number of filters, and you can increase the number of parameters in the convolutional neural network. Similarly, instead of using a single attention, you can have multiple attentions, or you can learn many stuff in the data set, right? So when you are taking attention, that means you are taking attention on about a certain factor, right? For example, if suppose if you are learning about something like if you are trying to, so I am just taking this example, something like if you are looking at an image from a real estate, and if you are trying to predict whether it is it is having green color, whether it has enough free space, it is good in color, if it is looking old or new, or whether it is closer to the main road, and all those things, right? So there are different factors that you have to pay attention to evaluate that particular real estate. So in each attention, or the single head attention, you can uh, evaluate on a certain factor, right? Like the green level of the house of this real estate. You can have another attention head focusing about the uh, free space around the house, something like that. So you can have multiple attentions, or you can have multiple single head attentions to increase the power of this model, right? So that is known as the multi-head attention, right? So in multi-head attention, it is a generic form of single head attention, where you can represent the single head attention with head I, right? Like this. So where you can with this head I, you can have the single attention for a particular q, k, and v value, right? So for each of these heads, that means for each of these attention heads, similar to the each of the filters that we are having different weight matrices, for different attention heads, you can have 3 different weight matrices, right? It's known as WIQ, WIK, WIV. These are weight matrices that you can define for each of the attention head. So once you give a certain query key and value, they have to be multiplied with each of these attention head specific weight matrices, and then you can generate, and then you can apply it into this attention formula and find the attention for that particular attention head. Similarly, you can calculate if the I is 10, then that means you have 10 attention heads. You can find 10 attentions for each of the heads. So then there would be 30 weight matrices, because each attention head would have 3 matrices that you have to maintain. That means WIQ, WIK, and WIV. Okay? So for each of the attention head, you have to maintain these 3 weight matrices. So these 3 matrices will be learned with backpropagation as usual. So the multi-head attention, the final multi-head attention is actually the concatenation of all these heads multiplied by another matrix known as W0. Right? W0, sorry, WO, which is output, corresponding to output, right? W output is also a learned matrix. Right? So for each of the attention head, you have to calculate with different weight matrices, and after each of the head is calculated, head 1, head 2, and head n, you have to concatenate all of them, and then multiply the whole concatenation with the WO, which is the output weight matrix corresponding to that particular multi-head attention. That is how the multi-head attention is giving this particular value, right, which is passed to the Adden normalization phase. So now look at the Adden normalization phase. In this phase, there are two operations basically, right? So one is add and the other one is normalization. So add, you know, right? So what is add? Add means you take this X input and we take that residual input, the same input, and skip this multi-head attention processing part and simply add it into the output of this multi-head attention layer, right? So we have done the same thing in the ResNet as well. The idea of this step is to add some identity value into the output so that when something goes wrong, that means if this multi-head attention would have a very smaller output so that this information will get lost. So by adding this value to the output, it would at least have an identity value of X would be added to the output so that information will not get lost if something happens inside this multi-head attention layer. So when you are developing a very deep neural network, these residual connections or skip connections are helping to maintain the stability of the learning process, because sometimes because these weights are changed randomly, right? So with some probability, some of the weights can get very small so that the outputs may get lost. In that case, the identity output would be maintained because this one is added to the output. So that is the advantage of this skip connection. The second part of this Adden normalization is the normalization part. Actually, this is a layer normalization phase. So we have learned about batch normalization, where you are taking the whole batch if you are using batch gradient descent, or if you are using mini batch gradient descent, we can use mini batches. But in this case, instead of batches, data batch, you are using the parameters in this layer, parameter values or the weight matrix values, and then you are normalizing these parameter values so that none of the parameters in this layer are not too large or not too small, right? So we are trying to make sure that they are following a normal distribution, right? So you may remember that we can learn two parameters, gamma and beta, for batch normalization, and similarly for the layer normalization you can have to learn these two parameters during the gradient descent or whatever the learning process during the backpropagation, right? This is what really happens in this Adden normalization layer. First we add the input directly to the output of this layer, and then we make sure it is normalized. Now let's move into the decoder part. So we have learned about the encoder, right? So we are not going to discuss about feed forward layer. We know what is feed forward layer, right? What it does is it to try to combine all of these concatenated outputs, and it would try to have a combination. It would try to do the real learning process happen in this feed forward layer, and it would also subject to this skip connection is add, and then the layer normalization process as well, right? Then it would be it would output the vector from the vector or vectors from this encoder unit. So if there are some other encoder units, that would also be given as the input for that particular encoder unit. So there would be n number of such encoder units, as you can see. After the n number of encoder units, you can find the outputs are given to the decoder from here, right? Encoded values are given to the decoder, right? The decoder, you can get the uh, shifted right input as the output, right? So that means, as I mentioned earlier, you start with the start token, and if there are any other tokens we have already predicted, you concatenate all these tokens to this output and give these outputs as the in from this point, and then you do the output encoding as similar as the encoder, and then you add the positional encoding, and similarly you go to this multi-head attention layer. But remember that in this multi-head attention layer, there's a term called masked multi-head attention. The idea is that unlike the multi-head attention that is there in the encoder layer, in the masked attention layer, you are masking the next tokens. That means if we are, for example, if we are going at the if there are three terms, right? Your cat is, if these are the three tokens that are there in this input, we have to mask. If these are the three tokens that are there, we have to mask other tokens that should be coming after, so that they are not learned by this decoder, right? Because decoder is a auto regression model, learning module, right? That means it should see only the previous inputs, your cat is, but not the next tokens that are coming after it, a lovely cat, right? These tokens should not be there. So what should happen is the softmax outputs related to this attention should be 0. For that, they have to be replaced with minus infinity before the softmax is applied, right? That is the difference between this is a special treatment that we apply on the input in multi-head attention, which is not done in the ordinary multi-head attention that is there in the encoder. After that, then we do the same add and normalization step here, and then we move into the multi-head attention in the decoder, right? So in the multi-head attention and decoder is also the internal implementation is same as the internal implementation of the multi-head attention in the encoder. But there's a difference. The difference is that in the multi-head attention of the encoder, you can see that Q, K, and V are equal to X, right? But when it comes to the decoder, K and V are taken from the encoder, and only the Q is passed from the previous layer. That means the query is passed from the previous layer, and the key and value, that means the context, is passed from the encoder that is there, right? This is the encoder. The encoder is passing, the output of the encoder is passed to the as K and V values to the multi-head attention. That is the difference between the multi-head attention in encoder and decoder. And this multi-head attention is known as cross attention, because one part K and V are from a different input, and query is from a different input. So what it really does, if you think in an intuitive way, is that the K and V contains, if you are, because this is written in the context of natural language translation, so the whole the meaning of the translation is actually there in this encoder, right? It is given uh, this encoder output in K and V contains the meaning of the this particular sentence. The Q contains the uh, contains the tokens that are already generated in English, right? KNV contains the meaning of the Japanese uh, language uh, sentence, the whole meaning, and the Q contains only the tokens that are generated in English, so that this should understand, yeah, now we have to generate this particular token, and then it would pass to the next layers and it would predict the next token that has to be generated in English. Okay? That is how the cross attention works with the help of encoder output. So this is how it really happens, right? So when this, if you want to translate this English sentence to Italian, there are main two tokens. One is known as the start of the sentence SOS token, and the end of sentence token EOS token. So the English, if you are trying to translate from English to Italian, the sentence starts with SOS and ends with EOS, right? And the whole sentence is given, I love you so very much, which is encoded with the encoding input, and then the encoder is processed and the encoder output is generated, right? And it is given to the decoder, and TMO molto. These are the words that are already generated, and the next word will be generated based on the meaning that is uh, given in this sentence in English, and depending on the words that are already generated from the decoder itself, right? So then the decoder output will be generated from here, and it will be mapped to the vocabulary using this linear layer. And once it is mapped, the next most probable token, or the English token, Italian token, will be generated from the softmax layer. This is how the translation happens in a transformer model. So when it comes to the transformer learning process, you can actually pass, not you don't have to train token by token. That means you don't have to uh, execute this process for all the tokens one by one. Actually, you can add them, add different tokens in a matrix, like SOS token, SOSTI, SOSTIAMO, SOSTIMO, Molto, and all these things in a single matrix, and pass it into the decoder input and get the encoder output. And in a one time step, you can get the softmax as an also as a uh, vector. That means a set of outputs, not as a single input, not as a single output, right? You can get all these outputs for each of the word combinations at a single time step. So this is a very fast task compared to uh, using LSTMs, right? With these transformers, you can actually do this faster when it comes to training. In this transformer learning process, you can use cross entropy loss because we are using the softmax classifier. However, you can use this one time step learning only for learning process. But when it comes to making inferences or when generating tokens, you have to generate tokens one by one. So for when you are generating a single token or single word, it's a single time step process, and you have to add that time token again into the output sequence and then generate another token. That is how you have to generate tokens when you are making inferences or generating new tokens, right? That is what you have to know when it comes to making inferences with the transformer. So now let's look at the different forms of transformers that are used in today's world. Right? So the transformers that is given in this original paper, attention is all you need, is actually about a natural language translation problem. Right? In this natural language translation problem, it is using a full transformer model, which is a encoder decoder model, right? But you can the the researchers have found that you can use not only both encoder and decoder together. Actually, you can use encoder only models and decoder only models as well, right? For different tasks. So let's see what are the different tasks that where we can use encoder only models and decoder only models as well. So the encoder models are also known as autoencoding models. Autoencoding means uh, encoder only models can understand something and get its meaning and encode it into a certain vector. That is the idea of using an encoder. So this is trained using the masked language models, pre-trained. So these models are trained with the which training process is known as pre-training. That means you can do something else after. You can train it specifically for certain tasks afterwards. But when you are training a transformer, you can use unsupervised learning techniques by using a huge text corpus, and you can uh, uh, remove some of the tokens randomly in the text and ask the encoder to predict what is the missing token. Right? That is the masked language model training process, where you take some random tokens of input sequence out and, or it is known as masking, and ask the model to predict what are the missing tokens are. Right? It is like grade 2 question paper where students are asked to fill in the blanks in some sentences. When students know about the language into a certain level, they can fill in the blanks and complete the sentences. This is what is asked to do when you are training an encoder only model, an auto encoding model. So the learned context with this encoder is known as the bidirectional context. So that means this encoder only models are learning in both of the ways. How that means not from left to right or right to left, but in both of the ways, how the structure is there in the sequence, not only in a single direction, but in both directions. So these kind of encoder models can be used for sentence classification. That means whether this sentence is happy or unhappy, something like sentiment analysis, or you can use it for other classification tasks like name entity recognition, which is also a NLP task, right? So you might have heard about some of the well-known open source models like BERT and Roberta. They are encoder only or auto encoding models. So now you can look at the decoder only models, which is also known as auto regressive models. In autoregressive models, that is used, they are using only the decoders of the transformer model. The learning process or the pre-trained process is known as causal language models or simply language models, where the model is asked to fill the last word of a sentence. So that is somewhat different from the previous one, which is masked language model. In masked language models, it is asked to fill some. It is the sum of the random words are removed in the middle of the sentence, middle or end of the sentence, and asked to fill that words. In the causal language models, always it is asked to predict the next word. That means the last word of a sentence, so that it can predict the next word when the previous words are given. So that is the idea of the autoregressive model, right? So this is also known as the full language model, right? So the difference between the context that is learned by the these kind of models is that these models can learn only a one directional context or unidirectional context of the tokens can be learned by these kind of models, unlike the encoder only models where it can have the bidirectional context. That means it doesn't, these decoder models don't have the two-way meaning, but it has a meaning learned in when the words are read in a certain direction, right? So there's a difference. So these kind of models can be used for generating uh, new text like natural language translation or summarization and something like that, right? Or code generation, all this generation stuff, the decoder only models are used, right? That is why most of the chatbots are using this decoder only model, and that is why they are get more famous in this generative AI world, right? So one of the most famous generative model is GPT model. Bloom is another open source autoregressive model. So when you have both encoders and decoders, this is known as a sequence to sequence models, which is exactly what is given in the transformer paper, the attention is all you need paper, where both encoder and decoder are there in the transformer. So how to learn it, it is dependent, right? It's subjective. Uh, one of the example model for this encoder decoder model is the T5 model, where so these learning techniques may depend depending on the model. There's no single way, but in the T5 model, how it is learned is that some of the set of words are some of the sequence of words are removed at once, and it is replaced with the single token known as a sentinel token, and the model is asked to predict the missing tokens. So this process is also known as pan corruption, when we are replacing the sequence of words in the middle of a sentence or text with the sentinel token, and then asked to reconstruct the original sequence, uh, replacing the sentinel tokens. So this can be used for similar kind of stuff, same as the decoder model, like translation, summarization, and questioning, answering. Uh, and this T5 and BART are some of the examples. Not BERT, right? This is not BERT. This is BART, BART. Right? This is a encoder decoder model. So when it comes to this question answering and translation and all those things, later that means this paper, the attention is all you need paper was released in 2017, but later researchers have found that decoder only models can do most of the stuff with much less computation and memory power. So instead of using sequence to sequence models, now they are using decoder only models, uh, very large decoder only models for uh, language generation, right? In tasks like translation, summarization, and questioning answering. That is why you see that not the T5 and BART kind of models are popular, but GPT kind of models are popular these days. So this is an extension of transformers for spatial domain. So we have discussed that the sequence models are so the transformer is an extension of the sequence models, but uh, depend because of its huge success, researchers have started to apply this transformer architecture for vision processing as well. So they have developed another model known as vision transformers, where in the vision transformers uh, can be used for image classification, object detection in the images, and image segmentation kind of tasks. So in this case, what it does is the image, it's a matrix of pixels. So it can be considered as a sequence of patches, similar to the words in a sentence. So these patches, that means the nearby pixels, are grouped together and applied so they are taken as a fixed size patches, like 6 by 16 by 16 patches. For example, if you take this image, you can divide them into small patches, and you can uh, apply it in a linear projection, flattened patches. That means these pixels in each of the patch are flattened. That means they are taken as a single dimensional vector, and then each flattened, that means single dimensional vector is given to the is considered as a token, which is similar to the word embedding token, which is added with positional and then it is added to the positional embedding, right? Uh, so this spatial information is given as converted into a single vector, and this is added with the positional embedding to maintain the spatial information, like this one, right? Like this uh, output, this flattened vector is added with the positional encoding, and then it is given to the transformer encoder, right? And then it can be used for classification task. So the advantages and disadvantages of the vision transformers as follows, like because the vision transformers are very good at working with very large amount of data to give better outcomes. So it is good in the way of scalability than for RCNNs, and it is flexible for different tasks related to vision. And but the disadvantage is it needs much more data. It's data hungry compared to CNNs, and it's much more computationally expensive, especially when you are using smaller data sets. So that's all for the today's lesson. If you have any questions, you can ask.